Okay, here we go. Hello. In period 3, I proved the mean value theorem. In period 4, I kind of screwed around a little bit and didn't finish. Period 6 tomorrow, who knows what will happen. But this doesn't or shouldn't take long. So what have we done so far? We've discovered Rolle's theorem, discussed it, drew pictures, proved it, discussed the mean value theorem. And yeah, what does the mean value theorem say? What is the statement of the mean value theorem? Well, if this function is continuous and differentiable, then what we need to prove is that there exists a point C on the interval a, b, such that the derivative of f at C equals f of b minus f of a over b minus a. This is the goal. Prove that this is true. Okay, and I need to do this, sorry about that, I need to do this for an arbitrary function on an arbitrary interval with only the assumptions that this function is continuous and differentiable. Okay, well, I think we should make a picture, sort of a big picture, and okay, I'm going to draw kind of a generic function, but there's also kind of maybe a story to this a little bit. Well, first let me just draw it in. And so we have, some function looks maybe like this or something. And okay, and the function, let's say, looks kind of like that. All right, and okay, great. So as we were discussing, there is this kind of function that I should be comparing my function to, and that is the function which goes directly from A to B. And all right, what I have to do is to prove somehow that there is a point, as we've been drawing, on this interval AB, where the slope of the tangent line to the function is equal to the slope of the secant line. Okay, how am I supposed to sort of understand this proof? Well, I'm going to explain the motivation for the proof by using an entire another story about the mean value theorem. This is the story of running a race. And okay, if any of you are long distance runners, you will know that when you run a big race like a marathon, say, or a half marathon, that you have to train for a long time in advance. You have to kind of build up your muscles, and you have to be in good shape, not just in your lungs, but on your sort of joints and stuff. And you're supposed to start training, months in advance. So back in 2002, maybe something like that, I was young and in very good shape, and I was living in the Netherlands, and someone I knew was running a marathon, and soon. So I was like, oh, I want to run a marathon too. That sounds like fun. And I looked, and there was a marathon that was happening in Amsterdam, and I said, okay, I'm going to sign up. And it was in a month or something like that. I don't know, maybe 6 weeks. So too soon. But I was doing a lot of other kinds of activity at the time, so I was like, oh yeah, I'll do this, it'll be fun. So just immediately started running 16 miles or something like that. And it was fine, I did it, it was great. And yet, I am not a super athlete, and so what inevitably happened is after a few weeks, I hurt my knee, and I got some kind of injury, which is the entire reason why you shouldn't try to train for a marathon in just 6 weeks. You should do it slowly. Well, I was very sad then, and it seemed like I wouldn't be able to run the marathon at all, and so I stopped running because my knee hurt so bad. And then, with a couple days beforehand, I was like, you know what, I'll just run the half marathon, and that will be fine. And that's what I did, and it was a success in a way. I had been training so much, my lungs were feeling good, and I was rested up, but I still had this knee problem. And so what we have here now is a picture of how my half marathon went, which is to say, I went really, really fast at the beginning. And if this green line is how you're supposed to run a marathon, what in fact I did was closer to this function f. How you're supposed to run a marathon, more or less, is you're supposed to train to run it at a certain pace, and then you're supposed to run that exact pace. And if you have trained to run the marathon in, say, 8-minute miles, then you should run at 8-minute miles the entire way. And then they tell you, if at the end, if you have anything in the tank, then maybe you can go a little bit faster. Okay, so what is this green line? This green line is the secant line. It's the linear function which connects the point a comma f of a to b comma f of b. And what does it represent in the context of this problem? It represents someone who ran the marathon at a constant rate. In fact, you even have these people, they're called pacers, this is my understanding, who run the race intentionally at a certain pace so you can keep up with them. So it's like volunteers or whatever who wear a big shirt with a giant sign on the back that says, I am running 8-minute miles. And if you know that you can run 8-minute miles, you can just follow them the entire race. It's sort of a volunteer thing. And okay, so this is kind of like someone who's running at a constant rate. What happened to me? I ran really fast, and with about 4 miles left, 5 miles left, my knee started hurting a little bit, and then it started hurting a lot. Then it started hurting so much that I was limping and walking, and it was actually quite embarrassing because I passed a huge number of people. And then one by one throughout the second or the end couple of miles of the race, people just passed me again, the people I had passed. And, it happened kind of in the way you would expect, right? So the first people I passed were then the last ones to kind of overtake me. And I remember someone with who was, with a giant knee brace on, kind of just crossed the line, just before me. Because I was really hobbling by the end. It was so bad. All right, enough personal stuff. Well, what is the point of all this setup? The point of all this setup is, what is this theorem really saying? This theorem is really saying that at some point at this race, I was going at the rate equal to the pacer destined to finish the race at the same time as me. In other words, I started at time A, I ended at time B, and the particular number of miles that I achieved were the miles between this location and this location, the 13 miles or whatever of the race. And so this green runner finished the race in the exact same amount of time as I did, but they ran it at a constant rate. All right, well, one thing we should do is figure out what is this green line after all. Well, we can draw kind of a picture, and the picture here is that the function changed by f of b minus f of a over b minus a. And of course that's then just the slope of this line. So if the slope of this line is f of b minus f of a over b minus a, what is the equation of this line? Well, the equation of this line, I say, is just a linear function, which has this as the slope and which goes through the point a comma f of a. In other words, this is the line y minus f of a equals, and then the slope we just said was f of b minus f of a over b minus a times x minus a. Okay, great. This is kind of a sort of a generic equation of the secant line through 2 points a comma f of a and b comma f of b. And okay, finally, I am going to write this green thing as a function. So I'm going to call this green line now a function. It's the function g. And what is the formula for this function? Well, it's just a function which is f of a plus f of b minus f of a over x minus over b minus a, times x minus a. Okay, so b minus a times x minus a. And okay, let's put a little box around that or something. And there it is. All right, so why am I creating this function? Well, the entire sort of idea of the mean value theorem is you're comparing sort of an arbitrary function on this interval to this function which goes directly, as I was saying in class. And this g function now is that function which goes directly. So looking back up at the top of the page, at the very thing that I'm trying to prove, what am I trying to prove? I'm trying to prove somewhere the derivative of my function is equal to the slope of this green line. But of course that's just also the derivative of the g function. In other words, just note that the derivative of g is just f of b minus f of a over b minus a, because it's a linear function. And so the derivative of this function is just the slope of that line. Okay, so after all this kind of setup and discussion, I now sort of see the light. Now the plan should be for me to show that somehow, somewhere, there's a point at which the derivative of f equals the derivative of g somewhere. If I can show that, then I have proved the mean value theorem. Okay, well, it's quite difficult perhaps to show that these two functions have the same derivative somewhere. So instead, we're going to pull this kind of trick, and it's this trick that we used already one other time in this class. It's difficult to show that two things are equal, but what we can do is to construct a new function which is the difference of those two functions. After all, I think I said this kind of more clearly in period 3, think about this, there are these kind of little gaps. What are these gaps? They are the gap between me, the runner who started out really quickly and then eventually slowed down, and the person who was running at a constant pace who was destined to finish the race at the exact same time that I did. So at any given point, I have a sort of a lead on this person who's going to eventually finish the race at the exact same time as me. We start at the same time, we end at the same time, and I have a gap on that person, and that gap kind of grows over time. And so what I'm now going to do is I'm going to give this gap a name. Call this function h. What is h? It is the size of the gap between me and the pacer at any given moment. For some particular x value, if I plug that x value in, it's going to land at some point on the g function, it's going to land at some point on the f function, and I hereby define this new function h to be the difference between those two. So let h be the function f of x minus g of x. And of course now I can take the derivative of this function, and what do I see? The derivative of this function is h prime of x is just f prime of x minus g prime of x. And so, if my goal is to show that f prime equals g prime somewhere, instead what I need to do is show that h prime of x equals 0 somewhere. And this should start to remind you of Rolle's theorem. In fact, the mean value theorem is just a generalization of Rolle's theorem, and our proof of Rolle's theorem was very, very low level. We sort of handled all that in the beginning of class. Now, the mean value theorem proof is kind of easy. In other words, we're going to use Rolle's theorem to prove the mean value theorem. And the way we're going to do it right now is by applying Rolle's theorem to h. That is the kind of big idea. Apply Rolle's theorem to h on the interval AB. Because, after all, what is the nature of this h function? This function which represents the gap that I have, the lead I have over this green pacer. Well, of course, the gap starts at 0, right? What is h of A? H of A is 0. What is h of B? H of B is also 0 because the gap is also 0 at the end. And so we start the race at the same time and we finish the race at the same time. And you can even confirm, well, that's just obvious. Okay, so what we have now is a function h. And what can I say about this function h? It's continuous because it's the difference of two continuous functions. It's differentiable because it's just the difference of two continuous functions. And it starts and ends at the exact same place. What goes up must come down. What does Rolle's theorem say? It says if we have a continuous function on a closed interval that starts and ends at the same y value, which is what we have here, then there exists a point C on the interval AB such that h prime of C is 0. And now that I've showed that h prime of C, so what have I just found? I've just found, I wish I had more colors. What I've just found is that there really is this point, looks like maybe about here or so, this point C. And what is the significance of this point C? The geometric interpretation of the mean value theorem is that the slope of the tangent line here to the point C is, or the tangent line, we can just say, is parallel to the secant line. So that's kind of one way of thinking about it. And now that I've shown that there's this place where h prime of C is 0, then I know that I have my point because, of course, let's see, I guess the simplest thing to do is just take this line right here. What is h prime of x? It's f prime of x minus g prime of x. And so if h prime of C is 0, then that means that h prime of C, which is just f prime of C minus g prime of C, I've just shown that that is 0. And so f prime of C equals g prime of C. And so I have, in fact, found a place in which the f function and the g function have the same derivative. And that completes the project because I've now shown that there's this point where the derivative of f is equal to the slope of the green line. And just to add a little bit of extra meaning to this proof, you can sort of, to connect this proof of the mean value theorem in this story to the proof of Rolle's theorem. What was Rolle's theorem? It was what goes up must come down. Or maybe better, if something comes up and comes back down again, then there is a place where it wasn't changing for a moment. There's a place where the derivative is 0. Well, here, what we've done to do this, to execute this proof, is we've applied the Rolle's theorem to h. In other words, we applied Rolle's theorem to the gaps. So I have these gaps. Well, what can I say about these gaps? Well, the gaps start really small, and then the gaps grow. The gaps get bigger, and then eventually the gaps get smaller. And so this special point, C, is the place where the gap is largest. It's the place where the gap stops getting bigger and starts getting smaller. And that is the place where h has a derivative of 0, and therefore that is the place where the f function is changing at the exact same rate that the constant g function is changing. Okay, so there's the proof. Sorry that was maybe a little bit too long. Goodbye.